Okay, we start. Welcome everyone to class 7. No, 8. 8, right. Class class 8. And you're going to be experts in production by class 9, yes. Okay. So first let's make a short summary. Okay, so last class was ESP. I gave you a small introduction. Then we talked about multiphase, which I told you is the most common case. We typically have multiphase flow. Even if the gas is relatively dry, it's still going to have some liquid, either from condensation or we will see later also from condensation of water. The, the, the pore, the gas when it's in the formation, if you remember most formations, they are water wet. Okay, so if you have the pore, you have some water around. Okay, and you have the gas. So water is wetting the rock, and then you have gas around. Okay. So due to the long time the gas has been there, just in the pore space, it has getting slowly saturated with water. Okay. And so my point is that even if the gas is dry, doesn't have condensate, you are still maybe very likely going to have multiphase flow due to this water. Okay. Instead of having oil, you're going to have water. And we are going to talk about it a little bit maybe tomorrow or the day after. Okay, so we first talked about this black oil model. We are going to see later that we can also do it compositionally, although it's a very heavy process, so it's not something you normally do in production. You try to make these tables with black oil properties to make it much faster. Interpolation is a very fast operation. We are going to see if you have an equation of state. Let me see if I put it here. No, okay. Okay, if you have, so black oil is used, okay, mainly for two reasons. Why? One, we have correlations are available. Okay, that's one reason. We can use correlations for different regions, for different fields, etc. It's also very fast to compute. Okay, I just have to make an interpolation. You just have to make bilinear interpolation. Remember, if you're a reservoir engineer, you have your life is easy. Okay, you interpolate only in pressure. Production, we have more complexity. Temperature is also changing. And also, the main strength that it has is that it gives you right away relates surface rates with local rates. Okay, it relates QO with QO at pressure and temperature, and relates Q gas with Q gas, pressure and temperature. So you have some physical meaning of all of these factors. How do you convert, or what happens with the oil from certain pressure and temperature to surface? Okay, so let's call it here fluid modeling. Okay, fluid model. That's what I say. Basically, this is to find how much oil and gas, okay, and to find also the properties. We will see for multi-phase calculation, we need density of the oil, density of the gas, we need viscosity of the oil, viscosity of the gas, and many things. Okay? So for that, I need a fluid model to tell me first if I'm one phase or two phase, and then to tell me how much do I have of each phase, and then to tell me the properties. and that I call a fluid model. And then the next step is a compositional model. Yeah, so let me open here just for a sec. And we're going to cover this slightly later, okay, maybe by tomorrow or the day after tomorrow. That where you probably saw van der Waals, you probably saw some other equations. Edit copy. Okay, where you use what is called a EOS, okay, equation of state. And you use it instead of using the C factor is not enough, okay, when you have two phase. It's fine for gases, but it's not enough when you have two phase. So you have to use an equation of state. This one that I'm showing here, I think that's Peng Robinson. Okay, Peng Robinson from 76. Okay, and you use it to estimate properties. However, we are going to see that that's a very expensive process. Okay, it's a very computationally expensive process. Because let's say to make one calculation, you have to first clear the V and you have to do a bunch of other things. You have to do some conversions there. Okay. Basically, yeah, I'm not sure if to go into it, but so if you have a liquid, right, and you have a gas, that they are in equilibrium. Let's try to make a small discussion on that. Okay. You have liquid and you have gas. Okay. And this has certain set I, which is the composition, right? Set I means C1 has some mole fraction, okay? C2 has another mole fraction and so forth. Okay. But the gas has a composition also. If you look only at the gas, has a composition Yi, and the liquid has a composition Xi. And to find that composition we don't know. The only one that we know is this. We know what I measure after the separator. I know what is the total composition of my fluid. But I have no idea at the given pressure and temperature how it's going to this Yi and Xi. And the way to know that is I use an energy that is something like the chemical energy called fugacity of each component. Let's say fugacity of methane. Okay, fugacity is just an energy. Okay, and if both of them are in equilibrium, okay, if the liquid is in equilibrium with the gas, the fugacity of the methane in the liquid should be the same as the fugacity of the methane in the gas or in the vapor. Okay, we call it V in the vapor. So I don't know Xi and Yi. Okay, I don't know if 30% of the methane went to the gas or 35 or 40, I have no idea. But I know that if they are in equilibrium at a pressure and temperature, then these two things, they have to be the same. Because if they are not the same, the methane will say, well, I have to give more energy to the one that is poor. Okay, it's like a socialist regime. I have to give what I have to the other one, so we will be the same. We will have the same fugacity. Okay. And this fugacity is a function of this equation, okay, as a function of the EOS. Okay. So the process basically is assume a Yi, assume an Xi, evaluate the equation, and calculate and see are these fugacities, these energies equal. They are not equal, then I assume another composition, I calculate another equation, then I calculate and verify and repeat. Okay, I have a, and that is extremely expensive process, very computationally expensive process. And you are going to do it by the end of the course. Uh, but just to say that that's not normally used so much to calculate. From here, you can really well calculate all of that. Okay, you can calculate all of that, but it's very expensive, so it's not normally done. People use tables, okay, for that purpose. So this comment was that even gas is dry, it will probably be saturated. You know what happens? That this tablet has exactly one line, like around this area, okay, where I type and it looks like my handwriting is not very good, okay? But when I write in that area, it's like this twilight zone. It's like it goes back to like 3 years old, okay? Like if I was learning how to write. So I have to stay away from this line, okay, from this region. From here to here is I cannot write anything, so it will probably be saturated with water. Okay, even though I have very little condensate, very little oil. So I still have liquid, so I will have gas plus water in the tubing. Okay. See, okay, then we talked a bit about, okay, we did an exercise. We found this matrix to convert, right? Very practical. You know now, if you use the simplified black oil approach, that's okay for many cases. You know how to use it. And if you have the more complicated black oil approach, also you know how to use it, as long as you have the tables, right? And you know how to interpolate. Um, yeah, and then oh, also one more thing. That black oil, let's make a space here under black oil. And it's also something that is extremely important. Okay, so let's take all of that, take it down. Usually is always a low GOR. Okay, so let's put it here. So simplified, okay, or let's call it not simplified, but traditional. Okay, it's called traditional BO. Okay, it's used for low GORs. Okay, we are talking here maybe between 700 all the way to 1500 standard cubic feet. And here I'm giving you some field units, so you're happy. Okay, we use it for non-volatile oil, okay, or also for dry gas, we use it. Okay, while the modified is called the modified BO, that you use for volatile oils. Okay, that means high GOR, typically from 1500s and above. Sorry, it should be like this. Okay, for gas condensate, okay, is very important. But you will see, you just see you plot your RS, okay? You calculate your small RS, you plot it, and then you see, well, it's too small, it doesn't matter. Okay? When you have a gas, yeah, you use the same. Yeah, you will have, in that case, you will have no big RS, but you have small RS. So you might have oil condensing from the gas, or we are going to see later for the water, you use another parameter called RS of the water. Okay, but we are going to talk about it when we talk about. But if the gas is dry, you can use BG. Okay, BG to convert between standard and local. Only when you have condensation from the gas of liquid, there you have to use a small RS. Okay. Okay, another comment I want to make here is that black oil correlation, so be aware, black oil correlations, you must always be tuned, okay, to laboratory data. Always, okay? Even though you are working, let's say, in the same field, the same conditions that standing was working, you have to verify with lab data, okay? Like, for example, you plot your RS, okay, versus P, and for T constant, and you obtain, how does it look like? That maybe it's going to be one of the questions in the exam, okay? How does RS looks like? And then you have to plot your points, okay? And you have to see where your points fall from the lab, okay? And you have to see if there is any deviation. Let's say in this case you have a deviation on the bubble point. This is the bubble point predicted by the correlation, PB, this is correlation, and this is the one that they measured. Okay? So in that case, you have to tune the correlation that we are not going to cover here in this course, but you have to tune it such that the line will pass exactly by the points. Okay? You insert a factor in the correlation and okay, you insert a factor in the correlation and then you try to match the data that you measure. Always, but you always have to plot and see how it looks like compared to data. Especially because of also the surface process. Okay, it might be that you have exactly the same crude that Standing used when he was, developing his correlation, but you're probably using another surface process, and that has an effect on the. Remember, the black oil table contains. So black oil table contains information about the fluid, okay, that's the first thing, how the fluid behaves, but also about the surface process. Okay, about both. So we have to make a table for whatever surface process we have. Okay, and then the other thing we had to discuss in class was this bilinear interpolation. We did an exercise. Oh, and actually I think I made this drawing for you. So we calculate all the parameters, BRS, MRS, BO, BG, interpolating in the table, and then that we calculate the local oil and the local gas rate. Okay, and I told you it would look something like that. So let's see, I think I made the homework. That is in the exercise. Okay, and that's the curve, that's what I wanted. Gas is the red one, the orange one, and just goes very small initially. You see it's almost zero. And that makes sense because when we did the PT diagram, we say it's very close to single phase oil. Okay? So it's all very, very close, but you have enough gas that came out of solution, and that's really that small gas that you have here at the bottom of the well. And then that gas is going to expand dramatically. Okay? And the oil is going to do the opposite because the oil is vaporizing and is losing mass to the gas. Okay, so the oil initially you had a very big rate, and then it lost about 30%. Okay, so the average BO is like 1.3. So let me put that on the notes, and that's one plot you have to make as part of the assignment. Okay, let's put it here. Okay, very much. The change in gas is extremely big. Okay, you see, oil is like a line, but this gas, it has the behavior with pressure. Okay, if you remember when we plotted with pressure, if this was pressure, then it has exactly that behavior. Okay, and after we did that, there was okay. Now we went a bit away from that. Okay, now you know how to calculate. Where is it? Here. Okay, now you know how to calculate local rate. We're going to use it very soon. I wanted to make a small comment on viscosity. We know it has some change with pressure, but the most important change is with temperature, because you have this wax problem. Okay, you have this wax issue. We talk a little bit about pigging and the complexities. Every time you have an oil flow line going from one place to another, the temperature will be reduced. You have to be careful. You have to check the wax appearance temperature, and if you're going to be below that, you have to do pigging. No other choice. Otherwise, you have buildup and it's going to block. Okay, and then we came here to the curve, the TPR for multiphase flow, and we are going to look today a bit more into that. But instead of going just from this point up, okay, it just has a minimum point. And that I explain because the pressure drop has two main components, okay, the hydrostatic pressure drop and the friction pressure drop. So in this case, the gas and the liquid is occupying less space. When it moves, when you increase the rate in the cross section, the liquid occupies less space and the gas occupies more space, and that is reducing the density of the mixture, and that is reducing the hydrostatic component, and that's reducing the delta P. But after that, if I increase too much the rate, the friction part starts to be relevant. Okay, it starts to be very big. So that's why you have this minimum point. The delta P will start increasing again. Okay, and then we talked that this causes some issues because you have two intersections on the curve, and I told you you have to be careful if you have this intersection, you have to give a push to the well such that it will try to tend to the other intersection. Okay, if you just try to produce it, it will go back below that intersection. Okay, so let's now continue a bit the discussion on TPR, and we're going to make also an exercise. Okay, so this is a continuation of discussion about TPR with multiphase flow. Okay, now let's paint our equilibrium. Okay, we are doing now bottom hole, PWF, versus rate of oil. Okay, when we have multiphase, we normally use the rate of the dominant phase. If the GOR is very high, that's a gas well, and you should use gas. So this is the surface rate of the dominant of the dominant product. Okay? If the GOR is low, then this is an oil well, and then you should use QO. But if the GOR is very, very high, then this is probably a gas well. And you should make the plot in terms of QG. Okay, but it's essentially the same procedure. So we have our IPR. We're going to talk about it tomorrow. How do we model that IPR? And then we have our TPR that I mentioned goes down and then up. And this TPR is, remember, for wellhead pressure 1. Okay, I fix the wellhead pressure and then I generate that curve. Now, what will be the effect of changing wellhead pressure? If you make the analogy with the gas case or with the liquid case, what did the wellhead pressure, changing the wellhead pressure, made to the TPR curve? It shifted, right? Yeah. We have two things. One of them was like scale up or down, but you keep the same axis, the same intersection point, right? But that was change of diameter, okay? And then we have that it can go up or down depending on the wellhead pressure. So if we decrease the wellhead pressure, it will shift down. Why? Because we should get more rate, right? So the intersection should move to the right. Okay, so if we shift, okay, like something like that, that's TPR for PWH2, where PWH2 is less than PWH1. And if we put a bigger pressure, okay, we are here on the upper part. Okay, very, very similar, but we have to be careful. There are some tricky things. Okay. Now, what happens if we add the GOR is changing? Okay, this is for a constant GOR is constant. Okay, now what happens? You know, for diameter will be the same, so I'm not going to make the same discussion. But GOR is interesting. It's something that we didn't have in single phase flow. We have it only in multiphase. How much gas? What is the ratio between gas and oil? Okay, so let's make another plot and see now the effect of GOR, okay, or Q gas divided by Q oil at standard conditions, okay, not at any conditions, that's standard conditions. Okay, so PWF, you see now I'm in the area where we have issues. Then we have one curve that goes like that, and we have this curve that goes like that. That is TPR for GOR1. What will happen, let's say, if I add a bit of gas to if now I have more gas circulating in the tube? If the GOR is a bit higher. If you remember, right, the delta P in the tubing has two components, right? Delta P of friction plus the delta P hydrostatic. We are neglecting now this acceleration change, okay? Just having these two. What will happen if I increase the gas? If GOR is higher, okay, the density of the mixture in the tubing goes down, okay, or becomes similar to density of the gas, and therefore delta P hydrostatic will go down. Okay, Therefore, the delta P of the tubing would also go down. Okay? Just because I have more gas, the density of the mixture is lower, and then the pressure drop is lower. Okay, so what will happen with the intersection, you think? If I have more gas, the delta P is less, therefore it's easier to flow, therefore to the right. The rate should be higher, right? Okay, so it does something like that. Okay, that's TPR GOR2. Okay, where GOR2 is greater than GOR1. And let's say I try another one and it does the same thing. TPR GOR3. Okay. Now, that process won't continue forever. Okay, it's not that I inject more and more gas and then I will get more and more rate. Because what happens? So far, this guy here, if I increase a little bit the GOR, this guy here, well, I don't change much. Okay, I just have more or less the same. Then I change more, I have more gas. What happens if I have more gas in the tubing? Okay, remember, gas is very much affected. It's exactly this plot that we saw here. Okay, gas is very much affected by pressure. Okay, so if I have too much gas, that gas will tend to expand. The local volume will be very high. And what happens if QO is very high? Okay, here QO is high. Sorry, Q gas is high. Therefore, VG, which is QG divided by A, will also be very high. Okay, therefore, the friction, delta P of the friction, would also be very high. You see? So it's not always good to have gas. I can use it, and at some point it's going to help me to, to reduce this guy. But be careful, it's also increasing this guy, and pretty much. So there will come a GOR where actually I will start to go back. The intersection will start to move again to the left if I increase the gas too much. Okay, so I will have, I'm not sure if I want to mess the figure, but let's say we have something like this. The intersection will start to go back. TPR, GOR4, okay, where GOR4 is greater than GOR3. So I have to be careful because I have this behavior, which you see the curve is like reversing. Okay, down, 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 and then it will start to go up. And yeah, I'm going to make a comment and let's see. Yes? Yes. I have more gas, but I have too much gas. Then the friction pressure drop will start to be too high, and then the intersection will go back to the left. Okay.
And how do we see that? Analyzing.
You have to run with different. You have to run with different. That's the experiment. Let's see. You can do it. We can do it with the exercise you're going to make. Okay, but okay, let's do. Let's present you something else. Do you know about gas lift? No? That you're also supposed to cover in the advanced course. Okay, gas lift. So in gas lift, let's say we have a well producing, okay, and we are not satisfied, okay, with the intersection. The well is producing with certain, Okay, we make our intersection, we have PWF versus Q oil, and the well is producing just here with certain GOR1. Okay. One method that we use, instead of using ESP, instead of using electric submersible pump, we use something called gas lift, in which we make an opening on the tubing, okay, and we inject gas from the annulus. And that gas is starting to go through this valve, okay? It's not so simple as that, but it goes through a valve and then it starts to come into the mainstream. So here now you have some oil, right? And you have some gas from before, okay? Let's say bubble flow. But when you go after the valve, you will have much more gas, okay? So what this guy is doing is basically making the column lighter, is artificially increasing the GOR of the tubing. Okay, just by injecting that. And therefore, I can have the behavior I showed you before. You can have that the curve now, the TPR will change, and the intersection will be to the right. Okay, I'm just injecting gas through the annulus. I have packer down, packer up, so the fluid can only go through the valve, and it gets mixed and increases the GOR of the tubing. Now, if you plot, okay, and that experiment we make in the field, or using a model, whatever you have. Yeah, gas injection, okay, that's the gas that I'm injecting. And here I'm going to plot how much oil I'm getting, okay. So the first part of this chart, okay, so here I have the natural, if I have no injection, what do I have? This is 0. I have this natural intersection, right? I have here, let's say it's Q is this guy here. Now I start injecting a little bit, I start to get more rate, right? I have to inject some more, I'm getting more rate, and so forth. But there will come a point where the curve will start to go back. The intersection already reached the farthest that it could to the right, and then it will start to go back. Therefore, the oil rate will start to reduce. Okay. So actually, it's not a curve like that, but it looks like that. Okay, so this is the GOR where I have TPR reversal, okay, at that GOR. So I shouldn't go above that point. I should just stay either on that point or to the left. Okay, so that's gas lift, and it's not the main topic of this course, but just to make you aware of that we can relate it to the effect of GOR in the tube. Yes? The objective is to make the density here. The objective is to make the density here of the mixture more similar to the density of the gas. Okay, and then you reduce the hydrostatic pressure drop. Okay. But if you add too much gas, then you have too much friction. So you have to be careful. You have to do it exactly at this point where you have the perfect balance between reducing the hydrostatic term and increasing friction. Okay, so I just want to show you how the curve looks like, okay, and this is a paper from 1954, and I think it's very interesting. It was a production engineer called Gilbert. Okay? He published a paper which was, became like a good reference in the industry, and he did many different things on that paper. He talked about choke, he talked about gas lift. That was a very big paper, had a lot of things. Okay, and he had, imagine in that time, 1950, no Excel, nothing. He published this curve, which it's amazing really how that these guys really could make such things, okay? It will be even difficult for us today to make that curve. Okay, so here he calls, can you see well from there? So here he calls, this is QO, okay? This is QO, and this is PWF. Intake pressure, he called it, but of the tubing. Therefore, it's PWF. And you see it has that behavior that goes down and up that we already know. Um, okay, so this axis is if you change, how does it change the curve if you change GOR? Okay, you see how that it becomes, I'm not sure if you can see from the figure, but it becomes a bit flatter. Okay, so it opens up to the right. Okay, it becomes flatter and flatter until more or less these points. These two, they have the same, on this section, they are more or less the same type of flat. Okay, and after that, it will start to go up and up and up. Okay, so it's exactly what I painted here. Okay, it's exactly this figure, but now you see it in 3 dimensions. Okay, not one on top of the other, but I'm painting it here. Okay, and then you see this point, which is here, that's the intersection with the IPR. So the IPR does something like that, okay? But here the intersection moves to the right, to the right, to the right, until it will just start to go back, okay? You will start to have a reduction of the rate. And here he says that's the optimum gas liquid, optimum GOR, and minimum bottom hole pressure. Okay? Really amazing. Okay, if that's clear, let's make let's use the first approach, something that even people still use in the field. Okay, something that is still used. We have now so many tools, but people still use this tool. Okay, so please take one. So you should take two sheets. Just take one of the first package and then take one from the other package. Okay, we're going to talk about a tool now that was used for many, many years, was a very good help for petroleum engineers, called, so to calculate TPR, okay, for multiphase, this is called pressure traverse curves, okay, were used. And for many, many years, and you can still use it, but we're going to see there is a fundamental limitation of these curves, okay, but we're going to see what it means. Pressure traverse curves. Okay, so that was made by, computers were only in a few places, or not many people had the tools to make the calculations you're going to make in Excel either today or tomorrow. Okay, so they pre-computed in a series of plots the following. Okay, so these are typically for vertical wells. Vertical well. By the 70s, we had really not many deviated wells. So typically it was for vertical wells. And you see all the curves, they start in zero. All curves start with zero. And you see this curve is made for one tubing size. Okay, so it's made for a diameter, fixed diameter. It's made for a fixed rate. Okay, is made for water, we haven't talked yet, but it's made for fixed water fraction, which is 50%, okay, and properties of the fluid, okay, gamma oil, gamma gas, gamma water, and the temperature, average temperature, something. For all of those, they pre-compute that curve, okay, and that curve tells you the pressure, and this is for different gas liquid ratio. Okay, gas liquid ratio is Q gas divided by Q oil plus Q water. Okay, but it's essentially the same. Okay, so they pre-compute if wellhead pressure is zero. Okay, vacuum. If I have all of these assumptions and they compute the pressure that the tubing, every point in the tubing will have. Of an imaginary tubing, I'm not taking any well in particular, a tubing that has all the way to 20,000 feet, which is a very long well, okay? Extremely deep well. 40 GBF. So they take, assuming zero wellhead pressure, and they went calculate P at 1,000, 2,000, 3,000, and so forth. For GOR, 0. For GLR, 0. Now they change, keeping all the rest the same rate, same diameter, same fluid properties, and for GLR 100. Okay, and they again calculate for every depth the pressure, and then 200, 300, 400, and so forth. Okay, and they included that. If we go to the original paper of Gilbert, let's see if I think I have it. Okay, and then you compute, you see what he has here. Let me see, I'm not sure if you will be able to read, but he says, if I'm producing with 100 barrels and 2.875 inch, I have this plot. Now if I'm produced with 200 barrels, I change the rate, I have another plot. And then I have another plot, 400, 600, and so forth. Okay, so I have to make a lot of work, a lot of calculation to calculate one plot for each. Okay, one plot for each configuration. If I change the rate, I have to create another plot exactly like that. Okay, now how do I use it? So you have there an exercise. Okay, the exercise, let's make that exercise together. Okay. And the exercise says, okay, you have a well, okay, where you have measured the bottom hole pressure, flowing pressure. The well depth is 9,000. Tubing 2.78 is producing 1,000 barrels per day. Water cut 50, and the GLR is 400. Calculate what this exercise says, calculate the wellhead pressure based on that. Okay, so the first thing we have to make sure that the table we have is exactly for this case, okay? That has the same diameter, it has, okay? It has the same rate, it has. It has the same water cut, it has. And we assume it has the same properties, okay? So all of that is the same that the case that we have in the field, okay? Let's say this is a well we have in the field. And then I have to check that the GLR is actually half the one that I need, okay, which is 400. It's here. Okay, so this is the line that I should be using. This line here, 400. Okay, so please could you tell me how much was it PWF? Can you read so I can copy the information here? PWF. I know the GLR is that's the example. The example we are doing is 262. The one from page 262. 400 standard cubic feet per standard barrel. PWF. How much is it? 2000. Hmm? It's here, okay? 2500. Okay? 2500 psi. How much is the well depth? 9000 feet. Okay? The true vertical depth of the well. And all the rest is the same. Okay? We have all the rest. Okay, so what do we do? How do we use this curve? Hmm? Any ideas? Okay, the curve that we want to use is this red one. Let's first mark it. Okay, is this guy here. That's the curve. All the others don't matter. Okay, we just have to look at that curve because that's the one for the GLR that I have. All the rest don't matter. Okay, so I'm just going to put it in red. Okay, so the first step I make, I come with the pressure I have. Okay, I have to come always enter with the pressure I have. The pressure I have is 2500 psi. So 2500 psi, it's how much? These are intervals of how much? 1, 2, 3, 4. No, this is 20. This is 26. So is someplace here. Okay, that's where I have 2500 psi. Okay, psi-g. I identify on the x-axis the pressure that I have. And then I go down vertically, exactly vertically, and I come down all the way until I find the curve with the gas-liquid ratio that I have. Okay. Exactly vertical. And then I move to the left to find the depth. Okay, how much is the depth that I get? Okay, it's like 11, 1,000, 200, 300, okay, feet. Now, what is that I want? Now I have to think about what I want, okay? What I want is wellhead pressure, okay? That's what I'm looking for, wellhead pressure. Therefore, the pressure I want is higher in the tubing, okay? It's shallower in the tubing. Therefore, I have to move up exactly the length that I want. So I say the TVD of my PWF is 11,300 feet. And the TVD of the wellhead pressure, P wellhead, is 11,300 feet minus 9,000 feet. I subtract. And then how much do I get from here? 2,300, yeah, feet. So that amount I come and I subtract, okay? I go to 2,300, which is here, and I intersect that curve. Okay, I identify, so that's the TVD of the wellhead, 2,300, and then I go and I read the wellhead pressure. Okay? It's not so simple to understand, okay? So it's okay if you're feeling confused. 300 psi G. Yes? 9,000 was not 9,000? 9,000, yes. Yeah, because this was made, people don't know about our well, okay? They don't know how deep is our well, what is our well. They don't know anything about the well that we have, okay? But they made all curves, they pre-compute all curves, assuming that wellhead pressure is the same for everything, okay? But you can still use it for our well. Even if our wellhead pressure is not zero, even if our well has less than 20,000 feet, we can still use the same curve. Okay? And the reasoning behind it is that if the fluid is the same, right? If the rate is the same, if the tubing is the same, at one particular pressure, I will have the same pressure drop. Okay? The same dP. So if everything is the same, the dP dx at that pressure should be the same for both. Okay, it doesn't matter if I'm looking, if now that pressure happens at 11,000 feet, or if it happens at 9,000 feet, or if it happens at 3,000 feet. It doesn't matter, the pressure drop is the same. And the pressure drop is what gives you the shape of this curve. Okay? So just to repeat, I come with the pressure that I have, okay, bottom hole pressure. I come and I find the line with the gas-liquid ratio that I have. I cross it vertically, and then I move to the left, 11,300 feet. That doesn't mean that our well has 11,300 feet, okay? Doesn't mean at all. But that is the bottom of my tubing, okay? Now I know that my well has exactly 9,000 feet, okay? And this is the bottom of the tubing. So to get to the top of the tubing, I have to take that number and subtract 9,000 feet, and now I have it here, okay? And then I go again at that depth, I knock the curve, and I come up and I read wellhead pressure. So my well will exist only between these 2 points, between here and here, only between these two, the well that I have. Okay? It doesn't come from zero, it doesn't go exist anything else, it exists only from here to there. But I have this pressure at the bottom hole, therefore the gradient is the same, and I have that pressure at the wellhead, and therefore the gradient is the same, and the curve is the same. Should we try another one? But this one you have to, I will help you, but you have to do it. Um, yeah, let's see the same, okay? Let's try another case. This is for you to make. If you're in the middle of the jungle and you have this book, probably you go to an old field, they have the handbook of production, you open it, you find a collection of these curves, okay? Just like in the paper of Gilbert. Okay, here you have a collection of those curves. So probably you can use it as a first approximation for your well, okay? If it's relatively same, if the data is relatively similar. So now let's see what happens if I increase the GOR. Okay? GOR is now 600. Okay, and let's say that 600 and the bottom hole pressure is still 2500 psi. Okay, then I want to ask what is wellhead pressure? Okay, GOR 600, another case, pressure of 2500. What is the wellhead pressure? Okay, so I give you time, so you think about it, and then we discuss it then, okay? So the first case, okay, we already understood, 2500, right? We come here with 400, okay, the red curve to the left, 11,000, and then we have to go up. We are at that point, we're at the bottom hole, then we go up. That means 2,300, and then we read pressure. Pressure is around 300 psi. No problem, easy peasy. Next one, now 600, so we have to use a different curve. We have to find 600 and mark it, and the same bottom hole pressure. Okay, so I come 2500, I knock it with 600, go to the left, I obtain 12,800, and then I have to move up. I have to subtract. I get 3,800 to the right again, and then up 500 psi. So far, no problem. Okay, easy peasy. Now comes this one, which was the cause for problems. Okay, bottom hole pressure 1600, GLR 200. Again, come here, 6,800 minus 9,000 minus 200. Okay, so what does it mean? If we continue this plot, right, and we do something like that, here will be minus 1,000, minus 2,000, okay, it will be someplace here. And you see, what is the sign of the pressure? I will need a negative pressure. I will need to have suction in the, that means that, and the minimum pressure I can have physically is just simply atmospheric pressure. That's the minimum. If I open the well to the atmosphere, that's the minimum it can have. What does it mean? Can I produce that rate or not? 1,000 from that well with that pressure? No way. No way. Because to produce it, I need to have a pressure which is less than the atmospheric pressure, which is not possible. I cannot produce. So the solution here was a trick question. Actually, was I cannot produce this well. Okay. What do I have to do? That's one solution. But if you see, you can suggest something. Okay. What is the, how much gas do I have to inject to be able to produce this well?
No, until the difference means the
Let's say this well is producing, right? Let's make a calculation. Q oil is 1,000, okay, standard barrels per day. How much is Q water? Is 50, so it's also 1,000. It's producing 50-50. And Q gas, how much is that? Is 200 standard cubic feet per standard barrel times QO plus Q water, right? So it's the gas liquid ratio times the Q liquid. And the Q liquid is simply Q oil plus Q water. So how much gas do we get here? 200 times 2000. How much gas is that? 400,000, okay? Q gas. Cannot flow. No way. Now your manager tells you you have to make it flow. Find a way. I want to produce those 1,000 barrels. If not, you're going to be fired. What do you do?
official
Artificial lift, right? I have to give energy. So let's do something. Let's do something. Let's assume that we can somehow you tell your manager, well, I need to put atmospheric pressure at the wellhead. Okay? Here. My well has 9,000, right? 9,000 feet. So my well will be here. Yes? And I know I have to, my tubing pressure, my bottom hole, flowing bottom hole pressure is 1,600. Okay? Yes? So the only way I can produce that rate is if the gas liquid ratio of the tubing is 500, right? It's the only way. Assuming that I'm producing that I managed to put a vacuum, okay, a zero atmospheric pressure at the surface, okay? That is the only way. This is the length of my well, the depth of my well, 9,000, and then I come here, I know bottom hole pressure won't change, okay? I'm still want to produce this rate, 10,000. Therefore, I have to have a G gas liquid ratio of 500. How much is that in gas that I have to inject? Okay, so Q gas total, right? Now, we found that a gas liquid ratio is 500. This is required. So the Q gas will be 500 times 2000. That means that's 1 million, 10 million, no, 1 million, 1 million, no? Okay, that means how much gas do I have to inject? The difference between the original gas that the formation is producing, right, and 1 million. So Q gas injection has to be 1 million minus 400,000. That means 600,000. So, okay, I was not fired by my manager. I found a solution. 200, where? is this one, right? Let's repeat. Is that clear for all of you, or should we repeat? Repeat. It's clear, very clear. Okay. We came with 1600 and whatever comes from the formation. Okay. Let's say that the GOR, if you produce with any artificial lift, that is 200. Okay. We made the calculation here. That means N is 50% water cut. Therefore, it's producing 1,000 barrels of oil, 1,000 barrels of water, and is producing 400,000 standard cubic feet of gas. That's the well that I have. If I want to produce that rate, I came to my plot, okay, with the bottom hole pressure. I can calculate this bottom hole pressure from the IPR, right? Because my manager, remember the IPR is like that, okay, Q oil and PWF, and my manager says I want 1,000. So I come here with the IPR plot only, and then I read bottom hole pressure, and that gives you 1,600. And they say, well, that's the pressure I need to have. Then I come to this plot, 1,600. You have to intersect with the curve of 200. Okay. Then you go to the left, and you get a number which is less than 9,000. Big problem. That means that to be able to flow that rate with that pressure, I just have to put vacuum, negative pressure. Not possible, no way. Okay. Now you see that if you increase the gas liquid ratio, if you increase it in the tubing, you see that the intersection goes lower and lower and lower. That means that it goes deeper and deeper and deeper. Okay, so you go exactly to the minimum. If I somehow manage to put the wellhead pressure at atmospheric, let's say, okay, just an exercise. If we do it, then the point at which I have that, okay, I get exactly here 9,000, so I will get here exactly 0. That's for a gas liquid ratio of 500. Okay, and if I now have 500, a gas liquid ratio, that means that I have 1 million of gas. But remember, the reservoir here is only producing, the reservoir is only producing 400,000. Okay, so where is the rest going to come from? The rest of the gas. To get exactly 1 million, I need 1 million to lift it. Okay, it's going to come from the gas lift. Okay, it's going to come from whatever I inject here. Okay, so you're going to have coming from the reservoir 1,000 barrels, okay, of oil, Q oil. You're going to get 1,000 barrels of water, and of gas you're going to get 400,000 standard cubic feet per day. But what you inject here, you're going to compensate and get the extra 600 standard cubic feet per day. Okay, such that inside the tubing you have a million. QG is a million. Okay? Should we make another one? Yes? Yes? The efficiency? No, no. No, no. That's no, this is not like a pump. You don't have efficiency here. It's just the gas liquid ratio. No. The only thing is if well, we cannot put at atmospheric pressure, okay, the wellhead. It has to be usually 30 bar, 400 psi. Okay, so you will have. Well, you do that exercise now. Let's see what happens if. Okay, let's make one case here. Okay, I want to produce 1,000 barrels of oil. I have a PWF of 1600 psig, and my wellhead pressure is, let's say, I think 120 psi. Okay, what is the gas liquid ratio, or what is the Q gas injected to produce the well? Okay, so I'm going to give you some time to solve exactly using the same plot that we have here. Okay? You have to do it. Are you going to solve the exercise now? Okay, so you might have you might have another way to do it, right? Just do it the way you understand it better. So what I did first, I took the two pressures. Okay, now the two pressures are given. That's not very typical, right? Only when we have gas lift, when we can change the gas liquid ratio. Okay, when I cannot change it, I just take one pressure. Okay, so I take both pressures and I draw a vertical line. Okay, for both pressures, 120 wellhead pressure and 1600 bottom hole pressure, such that they cut all lines. Okay, now I say, well, for 120, let's start with that, which is the easiest. Okay, if there is no gas, okay, the gas liquid ratio is 0, then I will cross here, right? But for all the other gas lead ratios, for all the other family, I'm going to cut more or less there, okay, in that point. When you go to the left, you find that this is 1,000 feet. That's the wellhead. Okay. Now I know the bottom hole is 9,000 feet down. Okay. So I come down 9,000 feet exactly to 10,000. Okay. So 10,000 is 1,000 plus 9,000. Okay. And then I say, well, the bottom hole pressure has to be exactly 1,600, right? So now I intersect that horizontal line with that vertical line, and then I find exactly the curve, the gas liquid ratio that I need to have for that intersection to happen, okay, which is 800. And then the rest is just math, okay? I take 800, calculate the amount of gas, and I know that the reservoir is just producing 400, okay? Therefore, the rest has to be injected in the gas, 1.2 million, which is a lot of gas, okay, that you have to inject just to lift that well. Okay, now let's make this last exercise before we go. And in this one, we have the wellhead pressure, okay? In this case, we have the wellhead pressure, which is 200 psi, and we want to find bottom hole pressure. You do exactly the same way. Enter with pressure, read the depth, and then you have to, instead of subtracting the 9,000, you have to add 9,000. So let's give you like another 5 minutes so you can. We have the same way, okay, that we did before. Wellhead pressure, 200 psi. We knock it with 500. Okay. Then we go to the left, and that means the wellhead, in this case, is at the depth of 2,800. We know the bottom of the tubing is 10,000 feet below that. So we have to sum, not to subtract. We sum 12,800. We reach here. It gives me 12,800. At least in my case, maybe I'm reading wrong. Okay. Then I go to the right. Again, I knock the same curve. Okay, with the same gas-liquid ratio. And then I come up, and then I say the bottom hole pressure of my well is 2000 psig. Very important how to use these curves, especially if these parameters they match your fluid. If you have a fluid which has similar behavior, perfect. You don't have to do any integration, don't have to know anything about multiphase flow. You just use that curve. The problem is these curves are made for vertical well, and these curves are made for, some fluid. If you change the properties, you have a different fluid, you have a different water cut, it doesn't work. Okay? But you have to know how to use it. Probably for the exam, you're going to get a similar exercise using these curves. Okay? So you have to practice and train. Just try to do by yourself this exercise we have done in class. Yes? Well, they told me there are going to be 2 exams. You're going to have 2 exams on this course. Professor, yeah, he's Rui Sitoe. He told me, huh? I'm writing the exam. Okay. For the exam, you don't have Excel. Okay, so we have to do something you can do by hand. This is something you can do by hand. Okay? Life is not so simple, sorry.
We found that the assessment is going to be the homework that you are giving to us.
Yeah, that's part of the assessment, but they told me you need to have exam. So that was like that last year. You had an exam, so. I don't know, I will send the exam soon. So they are the ones, they have to find a date. So I suggest I talk to Dr. Sitoe later and then we find, what are we going to do.
But before exam, you can send us a preparation.
Yeah, yeah. You will have a quiz and then you will have the final exam. What? Probably I'm going to do it probably.
So they will scan our answer.
Dr. Rui told me is that the evaluation will be for this course, at least that's what he told me. But we haven't discussed any more on the matter. Will be some home exercises that you have to deliver, and I told you in groups of 3, okay? Maximum groups of 3. And he told me also you are supposed to have 2 exams, okay? Exam 1 and exam 2. And the exam 1 is just like a quiz, okay? It doesn't account for much of the grade. And it's a preparation to take the second exam, which accounts for a big part of the grade. Okay? That we haven't defined yet. But I think last year we used something like 60-40 between the exam and the exercises, I think. And the quiz was only like 5 or 10%, I think. But I'm not sure what we are going to do this year. Last year it was Professor Ali who prepared the exam. This year probably will be me. And the correction, I think we did half and half, I think. So I'm not sure this year, I guess I will correct the exam. Okay, but it's still tentative. Okay, so we don't know. I have to talk to Rui.
Yes, but we are We have 14. We can mark all of them.
Okay, we will try. We will see. Let me see. Yeah, the recording is stopped. No, it's, so I hope Rui doesn't see our recording. So.
Because of the comments.
No comments. So, okay, let's do something else. Okay, we have let's now. This is another topic. Okay, I'm going to look more in detail at these flow pattern maps. Okay, flow pattern. Okay, I told you that we have a few flow patterns in the wheel. Those are configurations, right? What we discussed last time. You don't need a break, right?
No, it's very good too.
No break. Okay, good. Okay, let's see. Okay, we have, how do we call this configuration? A lot of liquid and some bubbles of gas. Bubble flow. Okay, then the next configuration, I start to increase the amount of gas. What do I get? Okay, I get something like that. How do I call this flow pattern? Okay, or this flow configuration? This will be churn flow. Okay. What happens now if I continue increasing the amount of gas? What do I get? I get batches of liquid with some bubbles of gas entrained, and I get a batch of gas, okay, with, okay. And finally, what happens if I continue increasing that how do I call that flow? Slug flow, or also intermittent flow. Okay, what happens if I continue increasing the amount of gas? I have liquid starts to accumulate only on the walls, and then I have a nucleus of gas in the center, okay, where I have these droplets of liquid. Okay, how do I call that pattern, that flow configuration? Annular flow. Okay, and that's what you find when you have an oil well, and these are what we call flow patterns. Okay, that's the scientific name it has, and many people has done a lot of research on that. So why do we care about flow patterns? It's nice to see how they look like, how they behave, but why do we care in production? Well, the way that we care is that each one of them, they will have a different density of the mixture, right? Which affects the delta P hydrostatic. And they're also going to have a different friction, delta P. Okay, you also will have certain different of the friction. So they are going to affect, in each one of these flow patterns, you're going to have different pressure drop. So that's why we care so much about flow patterns. Let me show you, I think last time I think we had some videos. I think, let's see if we can show them here. Yep. Okay, so that's a slug type flow. You see you have a package, some section of liquid, and then you have some section of gas. That flow, by the way, is very problematic for separators, because separators, they receive a batch of liquid, the level increase very high, and then they receive a batch of gas, batch of liquid and batch of gas. Okay, something else happened there, very strange. That's from a university in, I think it's in Switzerland. Now let's see this guy. Which flow pattern is that? We have, it's like a bubble flow, right? You have to see the bubbles, but you see at some point, you see that some slugs of gas go through. So it's like a slug between slug and bubble flow. And yeah, bubble flow. Let's see what else do we have. That's bubble, okay, pure bubble flow. Let's see this guy. What do we have? What flow pattern is that? Annular flow. Okay, we see the gas is flowing very fast in the center, and you have the liquid going through the walls. That you see, it makes like a effect on the with the light. Okay, so they are very important, the flow pattern, because they define the pressure drop. It's important to know where we are to define the pressure drop. But so you will see now the flow pattern depends pretty much on many things. Okay, it's very complicated. But you remember what have we done with when we had different regimes, right? Like for example, for the friction factor, if you remember, let's make here a comment. Remember single phase flow. Okay. What happens if, so how did we deal with these two regimes, right? With laminar and turbulent. How did we deal with that? We created an adimensional variable called Reynolds, right? And we use that to define if we are either to the left or to the right, okay, to define two regimes. Okay. We use the Reynolds number, and the Reynolds number is basically, yeah, a dimensional velocity. Okay. Of course, is the ratio between inertial and viscous forces, right? But it's also an adimensional velocity. So the researchers in multiphase flow, they had the same concept. They say, well, I need to use some sort of adimensional or some adimensional velocity. Okay? So they came with a concept. We have two phases, right? We have gas and liquid. So we have to have two velocities. So they say, I'm going to define some velocity, which is called the superficial velocity. And I'm going to use the USL for the liquid and USG for the gas. And how is that velocity going to be defined? Simply by USL is Q of the liquid divided by the cross-section area of the pipe, and US gas is Q of the gas divided by A. Okay? It's like if the gas and the liquid were flowing by themselves in the pipe with no other phase, just by themselves. Okay? But by doing that, then the next step they made, that's like my Reynolds. Okay? It's like this, not a dimensional, but it's a variable that represents how fast the liquid and the gas go in the pipe. Assuming that they go by themselves. Okay, you take a pipe. Okay, you know that part of it will be filled with gas, part of it will be filled with liquid. Okay, and then you assume that liquid is flowing by itself on the pipe and gas is flowing by itself on the pipe. And you calculate this superficial velocity. So if you plot, okay, USG and USL, okay, a plot just like what we did for the Reynolds, okay? But now we have two variables, the two velocities on each axis, and we use log scale, okay? That means here we have 1, 10, 100, 1,000, etc. 1, 10, etc. We will see the following. We have that there are a few very clear regions that I can define. Okay. A researcher came, okay? They came, this is for vertical pipe. They came and they had a pump, okay? They had a compressor. The pump took water from a tank, okay? They mix it. The compressor, we should put it the opposite way. Okay. We mix it and we put it on a pipe, transparent pipe, and this was done by many researchers for many, many years. And the researchers, they were here sitting, taking notes. Okay? So they tried with different combinations. They tried with different amounts of rates of gas and rates of liquid with different combinations. And they found that if they use a very low gas rate and very low liquid rate, they get, what flow pattern do they get in the pipe? Very low liquid and relatively low amounts of gas. We get bubble flow, okay, in this region here. And with very relatively big droplets, okay. What happens now if we make the liquid go a bit faster? Okay, let's say we have the same amount of gas, but now we make the liquid go slightly faster. It will start to break these droplets, these bubbles, into very fine, okay, very fine bubbles. And then we end up in dispersed bubble, okay, where we have very fine bubbles. Now, what happens if I increase the velocity of the gas? I go now the gas to go quicker. The gas starts to occupy a bigger space on the pipe, and we end up with the slug flow. Okay, we end up with slug on that, where we have intermittent flow of liquid and gas. If we continue increasing the gas, that gas is going to connect some slugs. Okay, it's not going to go alone by itself, but it's going to start to connect some slugs on the pipe. And here we have churn flow. Okay, that small section there. And if we continue increasing even more the gas, it's going to join all of these churns, okay, all of these blobs of gas, until it has a clear channel and it has annular flow. Okay, very low gas velocities, relatively high medium liquid. I have big bubbles, okay, bubble flow. Increase the rate of liquid. I have dispersed very fine bubbles. I have increased the amount of gas. Immediately this gas starts blocking the pipe, and then I have gas, liquid, and then I continue increasing the amount of gas. All of these slugs, they are going to be joined, and you have some blobs of gas coming up. And then finally, all of these blobs are joined in one, and then I have annular flow. Okay? And that was a big success, because now I could map, if I have some USL, okay, and USG, I can now map exactly where I am, okay, and I can calculate, depending on the flow pattern, I can calculate my pressure drop, okay. For example, for bubble flow, for this guy that I have here, the density of the mixture is simply, I can use density of the gas times Q gas over Q oil plus Q gas times density of the liquid, Q liquid or oil, Q oil plus Q gas. Okay. Simply like that. You can assume it's very homogeneous picture, and I can make an average based on the volumetric rate. Okay, this is very homogeneous. However, if I have slug, annular, I have that they is not exactly homogeneous, okay? So I cannot use that approach. However, there is one limitation. This map, the flow pattern map, also depends on not only of USL and ESG. People try for different systems. They try for oil, they try for water, they try for big pipe, they try for small pipe, and they saw that it also depends on the pipe diameter, depends on the inclination that you have, it depends on the fluid properties, that means density of gas, density of oil, because if you have a very dense gas, it behaves like a liquid. Okay, the two of them are more similar. So you have completely different map. Okay, viscosity of the oil, viscosity of the gas depends on the interfacial tension between oil and gas. Depends diameter, inclination, fluid properties. Um, yeah, the roughness of the pipe also. Okay, basically of those parameters. So we have a big problem. Okay, that's fine to have the map, and I could calculate if I have a case, but the map really depends on all of these guys, which is an issue. Okay. So before we continue a bit more on the maps, okay, what affects which flow pattern do I have? Let's make a short exercise, okay? Let's take the exercise we have been working on, which is exercise 5, okay, that we were working yesterday, and let's calculate. Okay, we calculate the local rates. Okay, now let's calculate the superficial velocity of oil and gas at every position in the tubing. Okay, so let's see what numbers do we get. Superficial velocity of oil, the liquid, what is it? Is the local rate of oil, right? Local rate of oil divided by the cross-section area of the pipe. Yes? So the cross-section area of the pipe, I think I put it here. Cross-section area. I have to block it. But be careful with one thing. We have cubic meter divided by square meter. That gives me meter. That's very fine. But then I have here days. So I have to change from days to second. How do I change from days to second? Yes. So we have to put here times 24 times 3600. Okay. Enter. And then I drag it down. We cannot drag. So you see the liquid velocity doesn't change that much. Okay. Well, it's changed much, but it's a very small number. It's 1.1. What is the velocity we normally have if we have single phase liquid on a pipe? What are typical numbers we have? It should be between 2, maybe 3, sometimes 4 when it's too high, but it's something between 1 and 3. Okay. So here we have, it's a bit lower than the values that we have normally in pipe. Okay. Let's do the same for the gas. The gas is the local rate of gas divided by the cross-section area which is here, and block it. Okay, and then I have to multiply times 3600, number of seconds in an hour, times 24 hours, number of hours in a day. Did you get similar numbers? Okay, the rate divided by the area. Now, if you go to the end, towards the end of the sheet, okay, I have this map, flow pattern map. Okay, this map, I have it at the end of the Excel sheet. So if you go a bit more to the right, you see flow regime, map data, but you should have flow regime, flow pattern map, okay? It's before traverse plot pressure. Okay, so you have, be careful, you know, the bounds will change because the properties are changing, right? Even though the diameter is the same, the inclination is the same, the properties are changing. If you see, let's go here to the left. Well, we haven't calculated the properties yet, okay? But the properties are going to be different. The viscosity will be different. So we cannot use the same, it's going to change slightly, okay? But if we assume that this is the flow map for that tubing, okay? You see what is the transition. So how do we go from here to here or from here to here? Let me just check that all the points are being plotted. Here we are plotting Q10 to 17 and P10 to 17. So that's Q10 to 17 and P10 to 17. That's correct. Okay, so let me take a snapshot of that. Okay, so now you have to tell me, where do I have the bottom of the tubing and where do I have the wellhead? Okay? What is the velocity of the liquid at the bottom of the tubing? We can find it here, right? Is 1.1. So the bottom of the tubing is here. Is this PWF, okay, bottom of the tubing. And I'm moving on this direction, okay, until I get to the wellhead. That means that for that particular well, initially I have bubble, and I start increasing the amount of gas, increasing, until I reach this boundary, okay? And then suddenly, I have a change of flow pattern, okay? It's not anymore bubble, but now I have slug, okay? So from this point on, I will have slug. Okay, when is that point in the tubing? Okay, when do I have this point? Okay, let's see, where do we have the transition? That's exactly when we have 1, okay, and this is like how much? It's like 0.2, I think, okay, 1 and 0.2. So the transition, yeah, no, 0.2 is log, okay. The transition, flow pattern transition between a bubble and annular and slug. Okay, we are transition between slug will occur at US L equal 1, around 1, and USG around 0.2 meters per second. Okay, so we can find exactly, actually I suggest we add one more column here. Okay, and we can call it flow pattern. Okay, let's call here flow pattern. Okay, so we said initially we have bubble. This will be bubble. This one will be also bubble. This guy, what do we have here? Okay, 1 and 0.3. We have exactly the transition. Okay, I think so. 1, 2, 3 is the third point. Okay, so that's where we have the transition. So this point, is not really, well, it falls where? It falls exactly on the line, okay? So this will be the transition, okay? And from all the points up from there, slug flow, slug and slug and slug. Okay.
So are those boundaries fixed values?
Are those boundaries what? Yeah, no. They change, like I mentioned before, with the properties, with the inclination, with many things. Okay. But for this one tells you that a big portion of the tubing, okay, only the first, only the first 500 meters or the last 500 meters will be under bubble. But after that, all the rest is slug. Okay, so a significant part of the tubing is under slug flow. Yes? Okay. So remember the flow, the map will change slightly. Okay, but the trend will change. Maybe this line will change a bit to the right, to the left. Okay, maybe this line will also change, but the shape probably will be maintained. Okay. So let me just copy maybe that so we have it. Okay. Yes. So just to show you how the flow pattern map is pretty much affected by the inclination. Is very affected by the inclination, pipe inclination. Okay. So, for example, for horizontal flow, okay, it will look something like that. And here we have some surprises. USG, USL, and we have two lines that are fairly and we have finally a line like this. Okay, where now we have another pattern that didn't appear in vertical flow. Okay, very low velocities of gas, very low velocities of liquid. The pipe is horizontal. Okay, what do you get? Very slowly. They are going to be completely separated. Okay, so you get gas is flowing at the top and liquid is flowing at the bottom, and that you don't get in a vertical pipe. Okay, that's called stratified flow. Okay, and that's here, stratified. Okay, what happens if now you increase the amount of liquid? Little bit of gas, but you increase the amount of liquid. Okay, the liquid starts to entrain the gas to get the gas in the core. So at the end you end up with bubble flow. Okay, where you have these droplets of gas, probably shifted to the top, okay, due to gravity, and then you have liquid. And this is called bubble flow. And what happens if I increase even more the velocity of the liquid? What happened in the case of the vertical flow? I managed to make these bubbles really, really, really small. Okay, so I get dispersed flow. Okay. Now, if I move to the right, okay, I increase the amount of, from stratified, if I increase the amount of gas, what will happen? Slug, right? We know slug is someplace there. But before that, we get what we get on the sea, right? What happens on the sea when it's blowing very hard on the wind is blowing very hard on the sea? You get waves, right? So that's the first step. Before having slug, you have stratified wavy. Okay, it's called stratified wavy. Okay, and that is basically we have some, and these waves can be very significant. Okay, and the gas goes like that. So that's stratified wavy. Okay. Here you have slug flow. Okay, when you have significant amounts of gas and liquid velocity. And what happens now if I increase very much the gas velocity? Annular. Okay, every time I have a very high gas flow, the liquid tends to be accumulated on the walls. Now you will have slightly more liquid down, not so much liquid up. Okay, and you have a core of gas that has some liquid, okay, inside, and that's annular flow. The main difference with vertical flow that you have this stratified regime, and you see the shape change pretty much, okay, the shape of the border. But you have the main change is these two guys, stratified. And I'm presenting it here because it's relevant for two things, okay? It's relevant for deviated and horizontal wells. So it's relevant for deviated and horizontal wells. Okay, these wells that where you have, they go like that, okay, and they perforate, that's your oil layer. Okay, and you have below, you can have water, okay, and above you can have gas. So in these wells, you typically have sometimes stratified on that section, okay, inside the pipe. And it's also important for transportation pipelines. Okay, so that's why I think it's important if we mention. And for inclined pipes, so what happens for inclined pipes? We have a mixture in between, okay? Depending how inclined it is, you have still stratified maybe 30 degrees, okay? But when you start going too much up, you don't have a stratified anymore. So you have a change, a continuous change, all in between. Okay, now what affects the change? Okay, why do we change from flow patterns to flow pattern? And be aware of something. Some changes, like for example from bubble to disperse, they are very, very gradual. Okay, I just increase the velocity of the liquid and it will start to make the bubbles more and smaller and smaller and smaller. But if you see here, the jump from here to here is very drastic. Okay, it's just a major jump. Okay, so we can make for the flow pattern, we can make the following. Okay, so this discussion is what affects the transition in the flow pattern map. Okay, the transitions in the flow pattern map. So I'm going to make it just for horizontal. So I have stratified. Okay, and if I start to increase the amount of gas, I get annular, right? Okay, I get annular. So I'm going to say here, if I increase, that's the direction of BSG. Okay, if I increase the superficial velocity, I have that transition. And these are basically flow patterns which are separated. Okay, which the gas and the oil and the liquid, they stick, they separate from each other. Now, let's go on the other side. What happens when we have low velocities of gas and low velocities of liquid? Okay, we have bubble flow, right? Most of the bubbles accumulated at the top. Okay, and what happens now if we increase the amount of gas? We get either churn or we get this log flow, right? So these two flow patterns to the right, I call them mixed, okay, mixed flow patterns. And this plot is just to tell you that the transition between separated is usually very gradual, okay, you go very slowly from one to another, and the transition within the mixed flow patterns is also gradual. Okay, you go more or less gradual. But when you try to change from this flow pattern to that one, is very abrupt, okay? It's very sudden. So the transition from here to here and transition from here to here is abrupt or sudden transition. Okay? Now the transition is given by flow pattern transition is given by the balance of forces in the phase, okay? Force balance or force equilibrium on the phase, okay? On the phase, that I don't write it like that, but it should be on the phase, either the oil or the gas, okay? Depending on the total forces that you have acting on that, okay? What happens in this case, in the case of stratified flow? You have gravity, right, acting on the liquid and on the gas. So, and you have really the velocity are relatively slow, okay? So gravity tends to separate the both phases. So in this flow pattern, gravity is winning, okay, against everything else, against turbulence, against kinetic energy, against everything, okay, it's winning. What happens in that case? You have a very good mixing, okay? Therefore, and gravity, so in that case, so you have, let's make it like that. So you have, okay, you have segregating forces, okay? So you have segregating forces, and you have mixing forces. Okay, what are the segregating forces we have? We have gravity, okay, gravitational acceleration. Okay, what else do we have? Interfacial tension, for example, right? Interfacial tension is what keeps really the droplet from breaking up, okay? So interfacial tension, okay? That's what really is keeping the droplet together, okay, or the bubble together. What else do we have? Segregating force. Okay, sometimes viscosity can be a segregating force, okay? Because it dissipates kinetic energy, okay? It's creating friction, and friction creates some segregation. Now on mixing, what do we have? Mixing, we have just the velocity, okay? Which is actually not a force, but how do we call this guy? Inertia, right? Okay. Turbulence, for example, that's also another. If I have a lot of turbulence, okay, I induce a lot of mixing. So you always have this fight in every flow pattern between these forces, okay, between these phenomena. And the one that wins is the one that defines how the flow pattern looks like. If you have segregation, gravity is winning, the viscosity is high, interfacial tension, they tend to separate. But if you have a lot of velocity, a lot of turbulence, you have a lot of mixing. Okay, so that's okay. Should we go? We have some more theory, but how is your brain? Tired, huh?
It's not really, we're a little bit sad.
Of the exam?
Yes.
Okay. Well, you have to have exam, right? It's good that we do exercise, but also we have to test if you're learning. Okay, so
But okay, I have one question.
yes.
Um, in terms of production wise, what is the impact of this different flow patterns? What is the impact?
The main impact is the pressure drop, okay? Remember, we want to calculate always PWF minus PWH. That's what we want, okay? This delta P. And depending on which flow pattern I have,
Okay.
I will have a different delta P. Okay?
So the impact is on the pressure.
It's on the pressure, yes.
Okay, and about the boundaries, how do I know the exact values for each?
They are, we are not going to talk about it here, but they are, if you make a force balance for the different regimes, you find the critical, it's like what we made on the droplet, okay? You find the critical force balance such that you have equilibrium in that configuration or not, okay? It's like, yeah, let's see. Like, well, I'm going to make a very, so if the gas phase goes very fast, right? Okay, it will tend, you have like a sucking effect. Okay, if the gas goes really high, really fast, then the the height of the layer of the gas is going to become smaller and smaller. Okay, then at some point, what happens if the height of the liquid touches the wall, the upper wall? You have a blockage, okay? The liquid comes in front of the gas, you have a blockage, and then the gas pushes that block. Okay, then you have slug flow. Okay, so the criteria for stratified flow is basically finding that critical gas velocity that pulls the liquid up and causes to block the pipe. Okay, in a very simple way, in a very simplified way. So we can make, and that's what we are going to discuss, I thought, tomorrow, okay, that you can make a force balance for bubble flow, and then you can see until which values that force balance still holds. Okay? If I have a change, then I will have slug flow, and that's how you find the transition. Also the same thing with stratified, and the same thing between annular and slug.
What is the desirable?
Well, the desirable is someplace in between, right? Everything has its good and bad. Bubble flow, what happens with bubble flow? The viscosity is the viscosity of the liquid acting on the walls, right? So I have high friction, and the density is also very high. Okay, therefore I have high friction and high density. Annular, the density is very low because you have the density of the gas, but the friction is very high. Okay, and slug flow, you have this intermittent flow. So just to, there is no really no good answer, but it's like in between. If you are someplace between bubble and between annular, that's where you have like the smallest delta P.
Between bubble and annular, it's slug.
Yeah, it's not exactly, because it's going to change. The amount of gas and the amount of liquid are going to change. So you cannot just stay in one flow pattern. Okay, but I'm saying that it's not that if you have annular or if you have bubble, it's bad. Both of them have, here you have more friction and you have less density, but here you have more density and less friction. Okay, and so if you take, for example, 1 point on both, they can give you the same delta P actually. Okay, and slug, you have this problem that is intermittent, so it's not really something that we like because it's intermittent. Okay.
And where do you place the stratified in the chart?
Well, this is vertical, so you don't have stratified.
Okay.
Okay, it's already 9:05. What I have left is I want to start some more theory I have to cover, okay, on multi-phase flow. There are some very important definitions we have to introduce. I'm not going to talk about all possible definitions, but basically the definition I want to introduce, if you see the cross-section of the pipe, okay? I look at the pipe cross-section, no matter which flow pattern I have, if I have bubble, I will have something like that, okay? If I have annular, I will have something like that, okay, for example, and then gas here. I'm not going to look at any of that, okay? I'm not going to be worried about that. What I'm going to do, I'm going to transform that into, I'm going to separate. This is a thought experiment, okay? It's not actually, I'm not going to do that in the field, but I'm just going to separate, okay? And do the same thing here. I'm going to separate like that, okay? And you're going to see, what you're going to see is that we are very interested, if you see the velocity of the gas and the velocity of the liquid, the real velocities depend on the area that the fluid is occupying, okay? They are directly Qg divided by the area of the gas, okay, this area that I have here, and the area of the liquid, the same thing. Okay, so it's not like what I did before, that I assume the whole phase is going through the whole pipe, but they actually go each one through their own area. Even though they're flowing like that, you just sum all the areas of the gas and all the areas of the liquid, okay? And you can just separate, just make it like that, okay? So these two guys, they are the ones that actually cause the friction pressure drop, okay? And the ratio in the area is what really gives you the density of the mixture, okay? The area of the liquid and the area of the gas, okay? They're actually the ones that define the density of the mixture. So what we are going to do tomorrow is to try to see how do I calculate those areas, okay? How much for each flow pattern, how much will the gas occupy and how much will the liquid occupy? That's what we are going to do tomorrow. And then we are going to do the exercise, okay? Because so you might think, right, that you say, well, the area of the gas is simply the Q of the gas divided by gas and the oil, right? It's simply like that. But it's not. That only happens for a few cases. This is valid only if we have homogeneous flow, okay? That means only if oil and gas, they travel at the same velocity. Only valid for that case. When, for most cases, they travel at different velocities, okay? Like if you are looking here, okay, at the vertical flow, okay, the droplets, the bubbles, they are, you know, they have buoyancy, right? So they tend to travel very, very quick up. So the velocity, they will go much quicker than the liquid. And that causes that you cannot use just this expression to predict how much the gas will occupy. No, you don't have velocity, but yeah. What I'm saying is that you have, yeah, let's do that tomorrow, okay? But just to, what I want to say here is that we are going to look at how much each phase occupies in the pipe, okay? How much the oil and how much, what fraction of the cross-section, what fraction of the cross-section is occupied by the gas and occupied by the liquid. And that fraction can give you many things. And we are going to use it to calculate pressure drop. That can give you the density and that can give you the velocity. Okay? But the thing how to calculate that fraction is tricky. It's not so simple. So we can use homogeneous, assuming that the velocities are the same, but in general they are not. So we have to use something else, and that's what I'm going to talk about tomorrow. Okay, so let's make a quick summary and then we go. Okay, we didn't take a break today, so it's okay that we leave a bit early. That's a summary from yesterday. Then we talk about TPR, what happens with wellhead pressure for multiphase flow. No change there. Now we saw something very interesting. For GOR, when I increase the GOR, the point goes to the right. But up to certain GOR, if I start increasing too much the GOR, I have too much gas, the friction becomes too high, and then the curve starts to go to the left again. Okay? And I told you if you do the experiment with gas lift, you inject, and then you inject, and then you inject, you will see that the rate from the well, the equilibrium will start to go back. So you have an optimum point for gas lift for a gas lift rate. We saw that these guys did it in the 1950s. Amazing how they did that. No computer, no Excel, nothing, and they generate that. Okay, well, maybe computer, but big computers, long time to calculate. Then we said, well, to calculate this point, okay, to calculate pressure drop, we can use pressure traverse curves. Someone in a computer or someone with a program took and compute for many different cases, changing water cut, changing the properties of the oil, properties of the gas, the temperature, changing the tubing size, changing everything. They pre-compute all of those curves, and we can use them to calculate bottom hole pressure or wellhead pressure. We can also use it to estimate how much gas lift we need, right? We use it here in this exercise. Very useful to determine how much do we have to inject. Okay, and I think this is a very nice exercise. And then we came into flow patterns. We tried to explain why they are important, why they affect the pressure drop. Okay, then we did this exercise of our well. Okay, we tried to see what is bubble, what is log. And then we just end up saying how these flow patterns are defined, but we are going to take a slightly different approach. Okay, we are not going to care too much about flow patterns, but we are going to use these areas, okay, how much the fluid occupies to calculate pressure drop. Any question? No? Okay, see you tomorrow then.